All right, so let's finish up this topic of effect of temperature on. Oh, sorry. So effect of temperature on the rate of a reaction. So last time we said that the projector is not on. All right, we said last time that the rate of a reaction typically doubles, okay, when you raise the temperature by 10 degrees. So typical room temperature is 25 degrees. So you go up to about 35 degrees, you double the rate. That's a rule of thumb, okay, but it's not exactly true for everything, but you know, it's a good gauge. It's a good guide for predicting how fast reactions would, how much faster reactions would go at higher temperatures. So if that is the case, what would be the typical energy of activation then for a reaction? So what was the equation that relates the energy of activation to the rate constants? Arrhenius equation, we said that the rate constant is equal to some constant A times e to the negative e sub A over RT, right? But if you want to compare two rates, we say that ln of K2 over K1, you take the natural log of both of these, would be equal to negative e sub A over R 1 over T2 minus 1 over T1. This is an alternate form of the Arrhenius equation if you just want to compare the rates at two different temperatures. Okay, so how am I going to solve for the energy of activation given this? I solve for energy of activation. So what do I do? I multiply both sides by negative R, right? Multiply by negative R. That would get rid of the negative R on the right side, right? And then what do I do? I divide both sides by 1 over T2 minus 1 over T1, right? 1 over T2 minus 1 over T1. That gets rid of that one. So that gives me energy of activation is negative R ln of K2 over K1 minus 1 over T2 minus 1 over divided by 1 over T2 minus 1 over T1. Okay? Think of it this way. This thing right here is really nothing more than the slope, right? If you were to plot, okay, if you were to plot natural log of K versus 1 over T, if you pick two data points there, points 1 and 2, okay, then 1 over T2 minus 1 over T1, that's the run, right? And ln of K2 minus over K1, that's the same thing as ln of K2 minus ln of K1, that's the rise. So negative R times the slope is the energy of activation. So let's plug in the numbers here. What would our numbers be? You'd have negative R. What is R? 8.314 joules per Kelvin per mole. What's ln of K2 over K1? Okay, we're going to call KT2 35 degrees Celsius, so that's going to be 35 plus 273 Kelvin. That's 10 degrees higher than 25 degrees. And we're going to call T1 25 degrees Celsius, so 25 plus 273, that would be 298 Kelvin. Okay? So if T2 is the higher temperature, K2 would be the bigger number, right? And what did we say? Typically, you go up by 10 degrees, your rate doubles. So what would be the ratio of K2 over K1? If it's twice as fast at the higher temperature, K2 over K1 would be equal to 2, right? Divided by 1 over, what's 35 plus 273? 308. 308 Kelvin minus 1 over 298 Kelvin. All right, so let's solve that. What is ln of 2? That's 0.693, right? That's 0.693. Okay. So let's pick up a calculator. Okay. So ln of 2, 2 natural log, that's 0.693, multiply by 8.314, 8.314, that's my numerator right there, divided by, parenthesis, 1 over 308 minus 1 over 298, close parenthesis. That's it. Equals negative 52,893. Okay, I'm just going to keep 3 sig figs here. So negative 528, negative 529, 52,900. Okay, so negative, that should be negative of the negative, right? There's an extra negative there. Oops, sorry. There's an extra negative there. So negative of negative 52900 joules per mole. Okay, your Kelvin here cancels out. The denominator will have a unit of 1 over Kelvin. You have a 1 over Kelvin in your numerator. So that's joules per mole. So that's about positive 53 kilojoules per mole. Like I said last time, typically reactions that, if you have reactions that double in rate when the temperature goes up by about 10 degrees, you're looking at an energy of activation of about 50 kilojoules per mole. Okay? So that would be a good number to remember if you have like to do a multiple choice test. That would sort of narrow down your choices. You look for something close to 50, but you know, don't assume that though. But that's typical. Okay. So let's see. That's it for this lesson.